Hello everybody, welcome back to my class. In this class, we'll discuss about monopulse tracking radar. The disadvantages of the previous two methods are conical scanning and sequential logging tracking radars. Is In both the systems, it requires minimum number of pulses for scanning and acquiring the data. Based on the acquired data, radar has to check and determine the future position of the radar. So to start tracking, it requires minimum number of pulses to extract the error signal. And tracking accuracy, which is very important, tracking accuracy will be degraded by the fluctuating target cross sections. Consider the cases when we are scanning a ship over the sea, which will have tides, which is fluctuating target signals. And if you are operating your radar in a rainy condition, the rain droplets will be fluctuating, so which will cause a fluctuating power in the received signal strength, which limits the accuracy of the detection accuracy of the uh, conical scan and sequential logging radars. Both the systems uh, gets affected by these fluctuating targets. Coming to the next, and the most important is both the systems need n number of pulses to start tracking. Now, this monopulse tracking radar, the target angle measurement is made on the basis of one pulse. So it is named as monopulse. In only one pulse, you will get the data and you can start tracking immediately. Unlike the previous system where you need to wait for n number of pulses to get the data for tracking. One pulse, a single pulse is transmitted using multiple antennas, and the error signal will be obtained. That error signal will help you to detect and to track its range, azimuth angle and elevation angle. All the three parameters can be tracked using by sending a single pulse. And here, because in the previous cases, in the first pulse of scanning, if I get some x amount of echo power, in the next pulse it will not be the same because of the fluctuations, where that is where the radar gets confused and the detection accuracy goes down. Here we don't have that issue. In only one pulse you can get the tracking data, so that problem will not be here in this topic. If you see this diagram, in this diagram we will have two beams which are given here in yellow color. This is one beam and this is another beam. These two beams are transmitted. Those two beams are added and subtracted, and the product of these two beams A and B and subtraction of these two beams A minus B will be multiplied in a phase sensitive detector to get the error signal. Here in this diagram, this lobe 1 and lobe 2 are transmitted. A pulse is transmitted in both the lobe 1 and lobe 2. The sum of these two pulses resultant is this center one, which is represented as sigma. Now the sum and difference signals are obtained like this and multiplied in a phase sensitive detector. See here in this diagram, two separate pulses, two lobes with a width of theta, beam width of theta are transmitted, and its spectrum is this. The sum of these two is shown here. This is sum pattern, and in the coming diagram you can see the difference pattern also. These two are the two lobes. The common area between the two lobes is removed, which is the difference pattern, and they are very narrow compared to the previous case. They are very broad, and it is very narrow because it is a difference pattern, and the product error signal if you plot the product signal, which is the error signal, it results like this. The error signal will be linear between some range. After some range, it becomes non-linear. We'll use the linear portion of the error signal to process the data to start the tracking. In this block diagram, you can see one angular coordinate monopulse amplitude comparison radar. In this, the duplexer which is used is a rat race junction. The beauty of this rat race junction is it will have two receiving antennas which will receive the echo signal. These two echo signals are given out in two separate output slots. One slot will have the sum of these two inputs, which is a plus b, example like a plus b, and in this channel you will have a minus b. Now the channel which is processing the sum is called as sum channel. The channel which is processing the difference is called as difference channel. A common local oscillator is used to heterodyne the received input signal, and this local oscillator supplies frequency to both the mixers of sum and difference channels. The output of the mixer, generally called as intermediate frequency, which is amplified by this IF amplifier, and the IF amplifier followed by a amplitude detector which will detect the range signal. The amplitude signal detects the range signal, and the phase sensitive detector, detects the angle error. Now this is a very simple block diagram which will have range signal along with angle error. This angle error may be used as azimuth angle error or elevation angle error depending upon the arrangement of antennas, receiving antennas that you took. So this is block diagram of monopulse one coordinate system. Now in this is two coordinate monopulse tracking radar. In this we are using four antennas here. Four antennas here. Two antennas will scan the elevation error, and two scan antennas. All the four antennas are used to detect elevation error and the azimuth error. I will explain you in the coming slide how two antennas help you to get elevation and azimuth error. Similar to the previous block diagram, it is also having the same setup like mixer, IF amplifier followed by an amplitude detector which will detect the range, and here also after the mixer local oscillator supplies frequency to all the three, and because this is a two-dimensional detector, it will have two channels, two difference channels. In one channel you will get mixer, IF amplifier and phase sensitive detector. Output of the first phase sensitive detector will be elevation angle, and the output of the second phase sensitive detector will be azimuth angle. And all these three IF amplifiers are connected to the automatic gain control. Because the circuit is complex, there is a tendency of getting fluctuations in the output, fluctuations in the amplitudes, which should not be degrading the quality of the output. So automatic gain control monitors the amplitude of the output of IF amplifier. Whenever the signal strength goes low, it will boost the signal and sees that it is stable. Now in this, two rat race junctions, one at the top and one at the bottom, are used because a rat race junction or a magic T will have 4 ports only, 2 ports for inputs and 2 ports for output. Output 2 ports, one port is for producing some signal, another one producing the different signal. Now these two are connected to the receiving antennas, and output of these two antennas are manipulated to produce one sum channel and two difference channels, for one for azimuth and one for elevation error. This is how a two coordinate amplitude comparison monopulse tracking radar works. This is the arrangement, simple arrangement of four antenna, two coordinate amplitude comparison monopole system, in which the top two antennas are named as A and B, bottom two antennas are named as C and D. Because elevation error is always the vertical projection of a antenna to measure the height of the target. So the sum of A plus B horizontally, top line, sum of top two antennas plus minus the sum of bottom two antennas. That means A plus B minus C plus D gives you the elevation error. And azimuth angle is the direction which is horizontal angle of a target. Now for this you need to add up A and C minus minus B plus D. A plus C minus B plus D produces the azimuth error. If the error is 0, then then we should understand that the antenna direction is properly aligned to the axis of the target. This is how four antennas helps you to have both elevation and azimuth errors for generating the error signal. Okay, I think you understood the topic. Thank you. If you have any doubts, you can leave a message in the chat box. Thank you.